Hello everyone and welcome back. Today we're going to continue our exploration of multiple linear regression and consider two mechanisms that can be used in order to detect which variables in a multiple linear regression model should be kept or should be removed based on its contribution to our model. So let's just go over a few basics that you definitely need to understand in order to work through these two concepts, which are known as the partial f-test and partial correlation coefficients. So we of course start with a multiple linear regression model. Let's assume it has the structure y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 all the way down to, say, beta p xp plus our residual epsilon. So in this particular picture, we have p predictor variables. All right, so usually what we do is we try to see, is this model with these predictors, x1, x2 down through xp, are they good predictors for this variable y? So the null hypothesis, h0, that we typically work with is that these coefficients, beta 1, beta 2, all the way down to beta p, of course the intercept is not one of them, all of them are equal to 0, with the alternative that beta I is not equal to 0 for at least one I. So that is our null and alternative hypothesis that we typically work with. So a couple statistical metrics that we use to test this are, first off, the MSM, which is equal to the sum of squared errors for our model divided by the number of predictors p, which can be found by SST minus the sum of squared residuals, all divided by p. And keep in mind, SST is just the variance of our response variables y times the degrees of freedom m minus 1 for those y values. And then we also have our MSE metric, which is just going to be equal to the error sum of squares, the sum of squared residuals, divided by n minus p minus 1. And if you don't remember how to find your SSE, you can always calculate the sum from j is equal to 1 to n of your observed y values minus your predicted y values, and then square each of those residual differences. Right? And that's going to give your SSE, and of course you divide that by n minus p minus 1. So from these two statistical metrics, we build what is called an f-test statistic, which is given by f-stat, which is equal to MSM, all divided by MSE. And as long as the normality assumption and independent assumptions are met for a multiple linear regression model, then both MSM and MSE will follow a chi-square distribution, hence their quotient will follow an F distribution. And in particular, it will follow an F distribution with P, M minus P minus 1 degrees of freedom. And obviously, since we're working with the alternative that at least one of them is not equal to 0, and this test statistic based on its structure and its direction, because typically MSM is usually greater than or equal to MSE, not always, but most of the time, as long as we have evidence for rejection. Therefore, this will be a right-tailed test. Therefore, if this is your F distribution, this is where your alpha is located, and obviously with that alpha is associated a F critical value. And then we can compare that F critical value to that F test statistic and then decide whether we reject or fail to reject this particular null hypothesis. So let's briefly outline what that conclusion looks like. So if the associated p-value, because from a test statistic we can calculate a p-value, if that associated p-value is less than our alpha value, then we will reject the null hypothesis that beta 1 equals beta 2 is equal to beta p is equal to 0. Which means what? Which means that at least, or all of our model coefficients, appear to have a good contribution to our model, right? And if the p-value is greater than alpha, or you could say greater than or equal to alpha, then we will fail to reject this null hypothesis that beta 1 is equal to beta 2 is equal to beta p is equal to 0, which means at least one of these coefficients is equal to 0. Right? In particular, the null hypothesis says that all of our coefficients are equal to 0, but it's possible that one of those coefficients are so close to 0 that it's pretty much weighing down the other coefficients in our model. So if at least one of these coefficients is equal to 0, or moreover, if all of those coefficients are equal to 0, one can ask the following question. So if some values of our beta, let's call it beta k's, are close to 0, is our model better without them? So that is the question that the partial f-test seeks to answer. Let's start off with a numerical example to sort of guide where this discussion is going to go. So let's assume that we have a multiple linear regression model with 3 predictors, x1, x2, and x3. As we already know, beta hat, which is represented by xtx inverse xdy, where x is the design matrix, first column of 1s, the rest is our data values for observed values of x1, x2, and x3, y our observed value vector, and sigma squared the homoscedasticity variance, which we should be able to approximate with the MSE, since that's an unbiased estimator. So with these two things that we know already, let's assume that these are the values in green. So beta hat 0, negative 36.7, standard error for beta hat 0, 13.5. Obviously, those are usually larger, but that's not the concern for the good contribution of our predictor conversation, right? So our focus is primarily with our beta hat 1, 2, and 3. So usually what we are looking for is predictor slope values, i.e. these beta hats, that are really close to 0. Obviously, if all of these values are close to 0, then we're going to be failing to reject that null hypothesis that all of them are equal to 0. But if this, or if the least value is significantly close to 0, in this case 0.52 will probably be the most closest of the three, then it's possible if that's really close to 0, depending on the unit and the standard error, then it's still possible that we will be failing to reject the null hypothesis, even though our other variables are, at least on the surface, contributing to our story. So, if that is the case, and our beta hat 3 is the closest to 0, a natural question that we can ask is, do we keep our predictor x3? Right? Now, it's very, very important to keep this in the back of our mind. x1, x2, down to xp could be in different units. Right? So for example, beta hat 1 could be in age, beta hat 2 could be in terms of height, beta hat 3 could be in terms of weight. But what exactly are the units for these beta hats? So let's actually take a look at our model. So if y is equal to beta 0 plus, say, beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon, and let's assume that our variables are x1, x2, and x3, and obviously that means y is a variable too, and we take the partial derivative of y with respect to one of our x's, say let's say xj, then that's obviously going to be equal to beta j. So the unit on beta j will be that of the partial derivative of y with respect to x. So that's obviously this beta j, in terms of its representation, is a unit change in our xj results in a beta j change in y, right? So if you change xj a lot, and your beta j is close to 0, that means it's not contributing to the story at all, right? So that's how we interpret these particular things. And obviously, so if we take, for example, x1 to be equal to age, x2 to be equal to height, and x3 to be equal to weight, then these beta coefficients are, for example, and let's assume we're trying to predict happiness in that vector y, then we have, for example, happiness over age, happiness over height, happiness over weight. And obviously, since they have different units, we should not be comparing them in their original form. So it's possible that 0.52 actually is not close to 0 with respect to the other two, because they would have different variances and different variance units associated to them. Right? So there are a couple approaches that people use. So I'll present both of them to you. So approach one to fix this issue is to standardize, or what people call standardizing, the coefficients. Standardize the coefficients. So what we do, keep in mind, beta hat j is already in the unit of y all over the unit of x. So if we can somehow cancel this unit of y from the top and the unit of x on the bottom, then we have a metric that doesn't have any units. So what we can do is we can define a new metric. I'm going to call it beta hat j with a superscript s for standardized beta hat j. This is going to be equal to our beta hat j from before that had the unit, but on the top we're going to be multiplying by the standard deviation of that random variable and the standard deviation of y on the bottom. Because when we multiply by this, the unit on the bottom is y, that's going to cancel with the top, and the unit on top is the unit of xj, which is going to cancel with the unit of xj on the bottom, and therefore this has no units. So that has no units. So that's one way you can look at the new coefficients and compare these. So we can compare different units, because if we use the beta hat JS, then they're not going to have any units, so it's fair to compare. Now, although this does fix the issue, it's usually not the more preferred way, especially if you plan to get other features for your model that is a little bit more advantageous. Obviously, this fixes one way, but it just fixes one thing in order for us to compare. So let me introduce another approach, which I find more appropriate. And instead of standardizing the coefficients, we standardize the entire model. And this actually gives us several advantages, which I'm not going to discuss here. So what we're going to do is we're going to define variable zj to be equal to the variable xj minus the mean of those xj values all over the standard deviation of those xj values. So therefore, keep in mind, before we had, for example, y is equal to x beta in terms of our matrix representation, which is, again, beta 0 plus beta 1 x1, all the way down to beta p xp. So what we're doing is we're taking our x values, we're subtracting the means of those observed x values and dividing by the standard deviation. So if x is normal, then this random variable is technically a t random variable, right? Right. So these coefficients beta hat 1, beta hat 2, beta hat p are going to change because our variables are going to change, because this has no unit. It has no unit. So when we standardize our variables, then we're going to have a new model. Our new model, keep in mind we're not changing y here, so we're going to have, for example, y. Now instead of beta 0, we're going to have a new variable. I'm going to call it zeta 0. And then we're going to have zeta 1 z1 plus zeta 2 z2 all the way down to zeta p zp plus the standardized version of our residual. Let's call it zeta epsilon. Right? So there are p standardized variables, and here we have the coefficients of our standardized model. So these are our coefficients of our standardized model, which are not to be confused with the standardized coefficients, where we just focus on the coefficients only. Right? Now, you will get the same predictions from each of these approaches, because technically you're not really changing the model in the first one, but if you use this model, you're actually going to have the same p-value, the same f-stat, Same R squared adjusted value, so you're not losing anything, but you have a different model. In particular, one of the things that change are these coefficients, and they will not have any units. And just as a side note, these coefficients are not the same as the standardized coefficients mentioned in approach 1. So keep that in the back of your mind. So this is still a multiple linear regression model, so you still can solve this with the usual approach. So obviously we're going to approximate our zetas with zeta hats. So our zeta hat is going to be equal to ZTZ transpose ZTY. Right, so that is going to be the solution. And keep in mind these zeta hats do not have any unit. So let's use the same numbers that we had before. So keep in mind we had, for example, beta hat 1, which was 26.3, beta hat 2, which was equal to minus 13.5, and beta hat 3, which is equal to 0.52. If you forget that these actually have any units, it's very easy to say, oh, I probably want to throw out beta hat 3. But you shouldn't, because they could be in different units. So we standardized these coefficients, and obviously we had a beta hat 0, but we don't really care about it. But it does turn into a new zeta hat 0, which is again going to be different, but that's not our focus. And we're going to have, for example, a zeta hat 1, which is like 2.61. You're going to have a zeta hat 2, which is negative 1.32, and zeta hat 3, which is equal to 1.83. Now, one important thing that's actually pretty interesting to sort of think about is the signs of our coefficients, both in the original and our standardized predictor model, will be the same sign, just different values, right? So if it was positive before, it's going to be positive again. If it was negative before, it's going to be negative again. But these do not have any units. Now here, you would look for the smallest value in terms of magnitude. In that case, that would be zeta hat 2. So based on this criteria alone, you probably would vote off variable 2 if you were to vote off something based only on this criteria. So now let's go back to our original model, which was beta 0, beta 1, x1, beta 2, x2, all the way down to beta p, xp plus epsilon. From here on, we're going to be referring to this model as our full model. Up to this point, we have a or possibly multiple criteria for deciding which variables to remove. So let's assume that we're at that stage of the story where we decide to eliminate E predictors. Here, E is going to be a variable. It's not the 2.71828 number. I don't have that many letters to work with, so let's just call E to be the number of eliminated predictors from our model. So what is the most or the highest value that E can be? So let's actually subscript these beta 1s with something. In particular, I'm going to call this beta 1 F, beta 2 F down to beta P F, and epsilon F to represent my full predictors, right? Because I don't have to choose these predictors, I can choose any subset of them, right? So in this case, I have P F predictors in my full model. So the maximum number of predictors I should be able to take away. Obviously, you should not be taking away all of them because then you're just going to be left with the lonely little intercept. Therefore, you don't really have a model. If you take away PF minus 1, that gives you a simple linear regression model. And if you're removing something, obviously, the number of removals should be bigger than 1. So from this logic, we see that 1 must be less than or equal to E, must be less than or equal to the number of predictors we're removing from that particular model. All right, so E is the number of eliminated predictors. Right? So if that is the case, the number of predictors, so let's do a little before and after chart, right? Number of predictors. So before we had, for example, PF predictors, and we're going to be removing E of them. So we're going to have PF minus E, which we're going to define as PR. And PR is going to be the number of predictors in our reduced model. All right. So when we have our reduced model, what exactly does that model look like? Well, obviously our response variable is y is not going to change. So we're going to have y is equal to alpha 0 plus alpha 1 x1r plus alpha 2 x2r all the way down to alpha pr x pr. Right? So this is our, let's not forget our little epsilon term at the very end. So these are our remaining E predictors, right? Which is a subset of the original, right? So for example, if we started off with 7, this model might have 5, might have 4, might have 2, might have 1, right? It might have 6, but it can't have 7, right? It has to have at least 1 less than it used to have, and it has to have at least 1. So from this set, obviously I've renamed my coefficients alphas instead of betas because they're not going to be the same exact coefficients because, we're going to have, possibly omitted variable bias, right? Because if we remove variables from our original model and those betas were not equal to 0, then those beta values are going to sort of spill out into these new alpha values in our reduced model. So how are we going to calculate these alphas? Well, that's still a multiple linear regression model, so we can still use the same unbiased estimator for those alphas. So for example, alpha hat is going to be equal to xtx inverse, but these are the reduced design matrices x, and then our xrt y. So from this new set of beta hats in some sense, then we're going to have, for example, a reduced SSE, a reduced SSM, and an SST. But keep in mind this SST is the same as before, right? So for example, SSE plus SSM always is equal to SST, but SSER and SSMR are most likely different, especially if those values are non-zero in whatever variables that we actually removed. So what's going to happen to our SSE? Is it bigger than before? Is it smaller than before? What exactly is going on there? So, as long as the removed, let's call them xj's, weren't identically zero, then we will have what? So as long as our SSE is greater than 0, which we typically assume that it is, else we have no variance to model, then which is going to be bigger, SSER or SSEF, where SSEF is the full SSE that we started with? You might want to take this video and pause it for a moment and think about this on your own before I tell you the answer. But the full SSE model is going to be less than or equal to the reduced SSE model, and obviously those are always bigger than or less than or equal to SST. So we always have this relationship, which means the SSE is going to increase when we remove predictors. But that obviously is going to lead to omitted variable bias because, as I already mentioned, those beta hat values are going to spill into those alpha values, and you're not going to see as much of a distinguishable effect in those particular predictors. Right? So you have this particular relationship, right? So we're increasing those SSEs, but hopefully we're doing it for a good reason. So let's take a look at what the ANOVA table for this reduced model actually looks like. So ANOVA table for our reduced model. So obviously we have our error source, our degrees of freedom, our sum of squares, and our mean square error. Right? So we have, since we're working just with one set of variables, we're just going to have one set of residuals. We have the error for our model, and then obviously we have the total error in our model. So our degrees of freedom for our total is not going to change. That's still going to be remaining at n minus 1. For our reduced number of predictors, that's going to be equal to the original number of predictors, PF, minus the number of variables that we removed. And then for our degrees of freedom for our residuals, that's going to be n minus p minus 1, which in terms of our original is equal to n minus the original number of predictors plus the number of variables we reduced minus 1. And if you're not sure why it's a plus, because technically there is a minus sign before we distribute that into the parentheses. So what I want to do is actually just write that as a minus and put a parentheses next to it, or you can just remove the parentheses and distribute the negative and make it minus pf plus e minus 1, depends on your preference and comfortability. Right? But that is your degrees of freedom for each of these entities, and that should be n minus 1, of course. So once we have our SOS, obviously we can calculate our mean square errors, but again, this is going to be our SSE reduced, and you calculate the same exact way, but you have different residuals now. You have our SSMR, and you have your same SST. So usually we calculate our SST or SSER, and we can calculate SSM by subtracting, or you could calculate it directly if you want, really no matter there. And lastly, once you have your SSEs and you have your degrees of freedom, just divide your degrees of freedom into your sum of squares and you can get your mean square error. So you're going to have, for example, a mean square error for your reduced model, a mean square error for your model, for the reduced model, and then you're going to simply have your MST, which is still your SST over m minus 1. So once you have your important metrics, MSE and MSM, then you can calculate your F statistic. So F stat is going to have the same structure, which is going to be your MSM all over MSE, but this is of course for your reduced model, and this will, as usual, follow an F, P, F minus E, comma, n minus pf plus e minus 1 distribution, and is still a right-tailed test. And as usual, the null hypothesis is that alpha 1 equals alpha 2 all the way is equal to alpha p r are all equal to 0. Now, hopefully you have a p-value that is not close to 0 or farther from 0 as before, because keep in mind what we're trying to show here when we're removing these models is that this model is better than it used to be, which means we're trying to reject that null hypothesis, right? Because our null hypothesis is that alpha 1 is equal to alpha 2 is equal to all the way down to alpha PR is equal to 0. So our goal is to reject if this is truly better. So if our goal is to reject, then that p-value should be smaller. If I misspoke before, I'm sorry for that. But the p-value should be smaller than it used to be. If it's not, then you sort of haven't really gained anything from that. But even if we do have a p-value that is smaller than before, for example, let's assume we had a p-value of, I don't know, let's say 0.07 for a full model, and let's assume we have a p-value reduced of 0.03. Obviously, if you have an alpha value of 0.05, that's going to be a better difference. You probably will be happy. But if this is our result, then we have more evidence to reject this null hypothesis, which may imply to you that this model is better than before. But technically, no, because keep in mind, we are not considering the other predictors that we removed in this hypothesis test. They are independent tests. So it doesn't directly answer that this model is better than before, but it can, in some sense, tell you whether this model is good or not for predicting the value of y, independent of what predictors you removed. So let's quickly address that and clarify that if need be. So what we have up to this point is two models, the full model and the reduced model. So we decide which predictors we want to remove from our full model, and then we can have these two independent hypotheses test, or testing the equality of our coefficients to 0. Right? So for example, let us assume that we fail to reject the first null hypothesis about the betas. So if we fail to reject the null hypothesis for our betas, then that means either one or many of these predictors are close to zero. Obviously, in the first example that I illustrated, it's possible that one is very close to zero and is dragging all of the others down. So if that is the case, then you probably would want to remove variables if one or more betas are close to zero. Right? Because if we remove those things that are close to zero, then most, quote unquote, are going to be not far from zero anymore because we removed all the ones that are far from zero. Of course, this leads to omitted variable bias, but sometimes you can address that indirectly with other advanced methods. Right? So that is one scenario where you would look into this. But of course, it's possible that we would reject the null hypothesis that all of our betas are close to zero, right? Which means we have evidence to believe that all of our betas are far from zero. Then in this case, you probably would still want to consider removing predictors to make our model better, right? Obviously, they're not far from zero, but we want them farther from zero, maybe, right? So there's two different scenarios of where you might want to consider removing predictors. Now, as I've already mentioned, the analysis of null hypothesis, beta is equal to the zero vector, alpha is equal to zero vector, these two null hypotheses are independent of one another, right? So one does not affect the other, at least not directly, right? So if we're using this particular model, it does not answer the question, is the model with alphas better than the model with betas in it? So that is the next question that I want to answer. So question, how to test the question, is model alpha better than model beta? That is, we're comparing directly these two models. So one way you can do this is what is called a partial F test. So I'm not going to go through the derivation of these particular things, but I will give you the F statistic and we can briefly talk about this. So the partial F statistic, which I'm going to call PF stat, is going to be equal to SSE R minus SSE full. Keep in mind, SSE full is always going to be smaller than or equal to SSE R, so this difference is always going to be positive, all over N minus PR minus 1 minus N minus PF minus 1. So what exactly does this term focus on? So we're seeing, has our SSE significantly changed? So that's what this is pretty much looking at. And we're going to be dividing this by our SSE full, because that's going to make it bigger than 1. And that's going to be divided by N minus PF minus 1. Obviously, there is some simplification that can be done here. For example, if we look at this piece right here, we're going to have N minus PR minus 1 minus N plus PF plus 1. Our N's are going to cancel with one another. Our 1's will cancel with one another. And this is just going to be equal to PF minus PR, which we know is just the number of variables that we eliminated. So we can actually represent this partial F statistic as the following. So PF stat can be equal to or represented as SSER minus SSEF all over E, where E is the number of eliminated variables, divided by SSEF all over N minus PF minus 1. Right? So that's a nice little way to write it. And you could also rewrite this in another way, but again, it really depends on what you prefer and what you're more comfortable with. You can write this as N minus PF minus 1 over E, so that's just our coefficient, times our SSER minus SSEF all over SSEF. f, right? I think that's a more nicer way of understanding sort of what's going on here. And this, as long as our assumptions are met, that both of them follow the normality assumption and independence, this is going to follow an FE n minus PF minus 1 distribution. And as usual, that would be a right-tailed test. So this test statistic, once you calculate your F statistic and the associated p-value, this is going to be testing the null hypothesis that there is no significant difference between our models, with the alternative is that M alpha is statistically different. Than our model for our betas, right? Which is usually what you want to do if you're trying to show that one is better or worse, depending on what other conclusions you got from the above analysis, right? But this is how to test whether this model is significantly different from each other. Because, for example, if your p-value just goes from 0.7 to 0.6, some people will say, that's not really that much different, right? 0.5 to 0.4, 0.3 to 0.2, 0.1 to 0.10, right? They are close, right? So this is going to help you decide whether there is a statistical difference between them. Before moving into the last thing that I want to mention, I just want to remind you of a couple correlation coefficients and coefficients of determinations that are commonly used in multiple linear regression, just in case you don't already know what they are. One of them is called, of course, the multiple correlation coefficient, which is just going to be the square root of the coefficient of determination. Some people just use the r squared value, some prefer to use just the r value. And some people also note this as y given a particular value of x. And this can be calculated via the square root of 1 minus SSE all over SST. Right? So that is our multiple correlation coefficient, and r squared, the multiple coefficient of determination. R squared always being between 0 and 1, and r always being between -1 and 1. And what this tells you is the strength of the linear relationship of y and a particular value of x, right? But keep in mind, we're in multiple linear regression worlds, so this x is actually a vector. So if I don't want to write this in an ambiguous way, one should actually write this as y given a particular value of x1, x2, down to xp, where x is the number of predictors. So that's a particular random variable. And then we have another useful metric, which is called the adjusted multiple correlation coefficient. And the only reason this exists is because as you increase the number of predictors, the SSE will go to 0 inherently, as long as you're not introducing just a bunch of 0 predictor vectors. But the adjusted multiple correlation coefficient tries to counteract that by changing the SSE over SST into MSE over MST. So the adjusted multiple correlation coefficient is, of course, going to be the square root of the multiple coefficient of determination, aka r squared adjusted, which is sometimes just abbreviated as just r, ADJ. And as far as I know, there's not a subscript for random variables, but I guess you could still subscript this with y given x1, x2 down to xp. Of course, the notation gets a little messy, but nonetheless, it's implied there. And that's just going to be equal to the square root of 1 minus your MSE all over your MST. Now, this is not often used, at least from my understanding, because the r squared adjusted value can be negative, and since we're taking the square root of a potentially negative number, it's possible that this might not exist, because you can't take square roots of negative numbers in the real plane. But you can always take the magnitude of that complex number and compare it to 0 still, but it really depends on what you're going for, right? And also, some people will use the notation r y given x as just the correlation between y and all of your variables. Or technically, you could say this is going to be equal to the correlation of y with your predicted variables. Now, what if you want to ask the question, or answer sub-questions rather, is there a good correlation between y and a subset of variables with potentially canceling out the interaction of the removed variables with the variables I'm interested in analyzing. So let's take a look at what that looks like. So this is called a partial correlation. A partial correlation. So let's just actually just write this down. So suppose we want to know the correlation between y and x1, but other variables, for example, say x2, might be influencing the relation between y and x1. So is it possible to sort of remove the interaction of x2 with y and x1 and sort of just have y and x1 alone, even though in some sense they probably are mixed together? Else why would we be doing a multiple linear regression model between them? So this partial correlation coefficient is going to be noted as r, let's do it y, and x1 with x2 held constant. So this is the partial correlation. This is the partial correlation with, or let's say of, y with x1 with x2, let's say partialed out, or phased out, I guess is a more appropriate word. So this is going to be calculated in a very interesting way, and you can sort of think about what's going on here if you have some theoretical understanding of the formulas. So this is going to be the correlation between y and x1. So that's just a bivariate correlation coefficient. So that's just a, y and another variable. This is not a multiple correlation coefficient. But you can extend that if you want to sort of know the correlation between y, x1, x2 with x3 phase out or something like that. So that's going to be equal to minus r x1, x2. Actually, here's a better way, I think. Let's do y with x2 and then r x2, x1. I think if I write it this way and you want to explore this on your own, this representation might give you a little bit of insight. And that's going to be divided by the square root of 1 minus r. Let's see here, what do we got going on? I think possibly a more safer way to write this is to keep in the same order as the top. So let's just write it as y x2 and then square that. Put that in brackets. And then 1 minus r x2 x1 squared. Because our rx1 x2 and rx2 x1 is the same exact thing, so that is a commutative. So this gives us the partial correlation of y with x1 with x2 phased out of the picture, right? So what exactly does that look like on our analytical viewpoint? So if we have y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus epsilon, and let's assume we're trying to remove this. Like we want to sort of phase that out, but maybe we don't have the time to run another multiple linear regression model. Maybe we can figure out, can we analyze what will happen between y and x1 if we were to construct a multiple linear regression model? Because if y and x2 do have a strong linear relationship, maybe we shouldn't remove x2. And if y and x1 have a strong relationship, almost like to 1 if it's an r squared value, maybe we should remove beta 2 because there's not much room to sort of contribute. Or maybe they're the same exact dependent variable or something like that. So one very interesting theorem is the following. If we consider the SSE removed minus SSE full divided by SSE full, this particular quantity, this is precisely equal to the r squared value for the model y, x1, with respect to x2 being removed. So let's put that square on the outside of that parenthesis. Right? So that's the partial correlation coefficient. Partial correlation coefficient. So that's interesting. So in some sense, they have a connection. So if that is the case, then you can actually calculate your partial f-test statistic in the following way, because this bracket should look familiar. So this is actually equivalent to doing the r-squared value for y x1 with x2 phased out squared times n minus pf minus 1 all over the number of variables that we removed. Now, keep in mind, if x2 really is a variable, then e is just equal to 1. But if x2 is a sequence of random variables, for example, x2 could be in disguise, beta 1 or beta 4, x4 plus beta 5, x5 plus beta 7, x7, where we're considering, removing 4, 5, and 7, and we're sort of phasing that out from the rest of the model, then in that case, e would be equal to 3. Right? But that's how you would conduct partial f-test and sort of how to calculate partial correlation coefficients, how to interpret them, and the connection between these two very important concepts. Hope you enjoyed this video, and I'll see you in the next one. Take care.